Okay, you should have two pieces of yellow paper in front of you. One that is not titled reciprocal parent functions, but it has cosecant on the front, and then graphing reciprocal functions. So we're going to start with the one that says cosecant. Also, you have a quiz tomorrow, even though it doesn't say it up here, over graphing sine, cosine, and possibly tangent. So be prepared for that. Okay, so we are here. And this is going, I already forgot, on page 109. So, page 109, when we're done. So if you remember, cosecant is 1 over sine of x. They are reciprocals of each other. They are not inverses of each other. Those are two different things. Your parent function for cosecant is going to be f of x equals CSC of x. So to show you where this comes from, we are going to very lightly, I mean, I can't really do it lightly up here because it's going to be a color, but I want you to very, very lightly sketch in a sine graph here. So sine would start at 0. It's going to go through pi and 2 pi and go in 1 and -1 right here. So very lightly sketch in this curve so that we can come up with cosecant. Do that over here as well, because I don't want this to overpower the other graph, but I want you to see how they are related graphically. So just light little sketch so you can see the curve. All right, and then let me fix that, make it look curvy. Then we're going to I just did the same thing. All right, it's fine. So we are going to come up with cosecant knowing what we know about sine and the fact that cosecant is the reciprocal. So let's think about what we have here. Right here, we know that the sine of 0 is 0. Well, the reciprocal of 0 is 1 over 0, which means it's undefined. So undefined on a graph is going to be a vertical asymptote. So instead of having 0 for sine, for cosecant, there's an asymptote there. There's also an asymptote here because that's at 0, and an asymptote here because that's 0. Same thing here and here. Okay. All right, so then let's think about what else we've got with sine. Well, this is pi halves. The sine of pi halves is 1. The reciprocal of 1 is 1, so the cosecant is also 1. So that point right there also exists on cosecant. Here, this is -1. The reciprocal of -1 is -1. So these points are the same. All right, so then we know we have a 1/2 value for sine. Think about what that would be. It would be the sine of pi 6. So pi 6 is like 2/3 of the way right here. So the sine of pi 6 is 1/2. The reciprocal of 1/2 is 2. So at pi 6, cosecant is at 2. And then here at 5 pi 6, it's also 1/2. So that would be up here at 2. At 7 pi 6, cosecant, or sine is -1/2. So then -2 for cosecant. And then the same thing for 11 pi 6. We're here at -2. So cosecant looks like what I have in pink. But curvier. It's a little too pointy, but I'm not going to do it again. All right, so it's like since it's the reciprocal, it's like the blue graph, or the sine graph gets flipped and turned inside out. So here this is at 2 and at 2 and at -2 and at -2. Okay. So where sine has zeros, cosecant has asymptotes. And where it has max and mins, we also have relative max and mins and those points there. Okay, so my pink graph is what should be dark on your paper because this is actually the graph of the parent function of cosecant. But I've also got pieces out here. I can do this one, and we can do this one. Oops. So let's talk about domain and range and all that good kind of stuff. So your domain, it's not negative infinity to infinity like sine was because there's a whole lot of stuff it can't be. So this is one of those weird ones where it's all real numbers, but we have to put everything it can't be. Well, it can't be 0, and it can't be pi or 2 pi. So basically every pi, so remember that is x cannot equal n times pi, where n is an element of the integers. The range, well, we're going from negative infinity to negative 1. You never include the infinities. We do include negative 1. And then we start back over at 1 and go to infinity. X-intercepts, which we will change to zeros. Actually, it doesn't even matter because, oh, that's not even a word there. Making up words now. Okay, zeros. Whether it's zeros or x-intercepts, it doesn't really matter because there aren't any, so it's none. Y-intercepts, none of those either. Asymptotes, yes, a whole bunch of them. And remember, the domain and the asymptotes are very much connected. The reason that x can't be these things is because that's where your asymptotes are. So x equals n times pi, where n is an element of the integers. The amplitude. Well, remember that's half the distance between the max and the min values. You don't have those, so this is undefined. The period before it repeats. So I've got up and down, so you got to have one of each before it repeats. So look at this, and just like sine was 2 pi, you've got 2 pi for cosecant. Okay, our transformations, so f of x is equal to a times the cosecant of b times x minus c plus d. Amplitude is undefined, however, I can still stretch the graph. So I still have a vertical stretch or compression that would be the absolute value of a. The period is still 2 pi divided by the absolute value of b, just like it is for sine. This is still c. This is still d. Okay. So let's look at secant. So secant is the reciprocal of cosine. Reciprocal, not inverse. So f of x is equal to the secant of x. So again, we're going to very lightly sketch in cosine. Cosine's going to go through here and here. Halfway in between is here. And then there's these. So I'm going to lightly sketch my curve, like so. Oops. And then lightly sketch this. There we go. Same kind of thing here. We're going to take the reciprocal of cosine. So at 0, the reciprocal of 0 is undefined. 0 is undefined. Here's a 0. It's undefined. This one's undefined. The reciprocal of negative 1 is negative 1. Of 1 is 1. Negative 1, negative 1. 1, 1. This one over here. So then I want the cosine of pi thirds. Pi thirds is like right here. And at pi thirds, it's 1/2. So the reciprocal of 1/2 is 2. And same thing happens over here. And this happens just like with sine, right? -2, it'd be right here and right here. And right here. Same kind of thing that happened with sine, because just like with sine and cosine, secant and cosecant can be made into each other just by a horizontal shift. So it looks like this. All right, there we go. Everything that's in purple is your secant graph. So when we look at domain and range, domain, again, is going to have to be all real numbers, but x cannot equal, right? So it's not n times pi. It does happen every pi intervals that you can't have anything, but we start at pi halves and then add or subtract a pi from that. So it cannot equal pi halves plus n times pi, where n is an element of the integers. The range, once again, I'm going from -infinity to -1, and then start back over at 1 and go to infinity. X-intercepts, whether I call them x-intercepts or zeros, it doesn't matter, there aren't any. Y-intercepts, I do have one here, and that is at 0, 1. Asymptotes, I got a bunch of those. Remember, it's related to the domain, so x equals pi halves plus n times pi, where n is an element of the integers. Amplitude is undefined because I don't have any max and mins, and the period is still 2 pi. Okay, so for my transformations, f of x is equal to a times the secant of b times x minus c plus d. Amplitude is undefined, but remember I can still stretch it. So I still have a vertical stretch or compression. That's the absolute value of a. Period is 2 pi over the absolute value of b. The horizontal shift, which is called phase shift for trig, is c, and vertical shift is d. All right, let's look at cotangent. So we know that cotangent is 1 over the tangent of x. So f of x is equal to the cotangent of x. So just like on the other ones, we are going to lightly sketch in our tangent. So for tangent, I start here, right, at 0, 0. My period is just pi. There's an asymptote right here. Okay, very lightly, very, very lightly on this. And then this is at 1, so it's going to come like this. Okay. And on this one, because I'm afraid this is going to get a little too confusing for you, instead of doing like the whole thing by sketching it in, I'm just going to sketch in that part, and then we're going to go from there. So I'm taking the reciprocal, okay? The reciprocal of 0 is undefined. So I have an asymptote here now. My pink asymptote is the real asymptote for cotangent. This was my tangent one. So make sure that's super light. Then reciprocal of 0 is undefined. Okay. This is undefined. The reciprocal of undefined doesn't have a reciprocal because it's not a number. But the reason this is undefined is because you're dividing by 0. So if you take the reciprocal of that kind of before it comes undefined, you get 0 there. Okay. And then for tangent here at, so this is pi halves at pi fourths, tangent is 1. The reciprocal of 1 is 1. So cotangent is also 1. For 3 pi fourths, tangent is -1. The reciprocal of -1 is -1. And so this is what one cycle of cotangent looks like. It looks like you have shifted tangent over and reflected it in the x-axis. Okay, but it does shift over because of those undefineds change where they are. Then we just repeat this because the period is pi. Goes here and here and here. Period is pi, so I get an asymptote here and here. These are these. Get 1 and -1. And I've got this. Okay, and this here and here. Okay, so there's the parent function for cotangent. What's in blue was tangent, or just part of it anyway. If I put the whole thing in there, this one would be really wacky. Okay, so let's look at our domain. Our domain is all real numbers except it can't be 0 or pi or 2 pi, so it's every pi. So all real numbers that x cannot equal n times pi, where n is an element of the integers. Their range. This is -infinity to infinity. The x-intercepts, I have a bunch of those. Okay, they start at pi halves, and then it happens every pi after that. So we're going to call them the zeros, so that makes it nicer. And we get pi halves plus n pi, where n is an element of the integers. Y-intercept, there's none because I have an asymptote there. Asymptotes, I got a lot of them related to the domain. So x equals n times pi, where n is an element of the integers. Amplitude is undefined still because there's no max or min. The period is still pi. Your transformations, f of x is equal to a times the tangent of b times x minus c plus d. Amplitude is undefined, but you can still stretch it, so you still have a vertical stretch or compression. And that's the absolute value of a. The period is pi divided by the absolute value of b. The horizontal or phase shift is still c. Vertical shift is d. So there's the basics of your reciprocal functions. So now we're going to graph them. So grab your other piece of paper. And this is going on page 110 when we're done. So here are the three, and the asymptotes are missing, so add those in. They're important. They belong there. Okay, get all those in there. Looks like it's raining on there. Okay, so we are just looking first at the basic ones. And it says the period of cosecant and secant function is 2 pi. The period of the cotangent function is pi, just like their reciprocals. Okay. So we have to identify the period and then graph each function. Okay, there's really more that we need to identify besides just the period. So there is no b here. This is cosecant, so my period is 2 pi. Okay, and cosecant is 1 over the sine of x. I do not have an amplitude. It's undefined, but this 3 halves, that is my vertical stretch. That is important to me for sure. And then I'm going to have a little sketch of sine here. Okay, so that I can think about what's happening. You could sketch cosecant right there. I really think just having sine, since you kind of know where they come from, is what's going to be helpful for you. So 0, 0. Okay, that's where sine starts, right? But it's the reciprocal, so since this is 0 here, this has to be an asymptote. So for cosecant, I have an asymptote at the beginning of the period, and there is one here at the end of the period. The period is 2 pi, so here's my outside asymptote. There's also an asymptote right here at pi. Okay. Halfway in between these two, I'm going to have a 1 and a negative 1, but this is my stretch, so that changes that number, and also if I had a reflection it would change it. But halfway in between here, I'm here. Parent function for sine and cosecant would be at 1, but the vertical stretch takes me to 3/2, which is 1.5, and there's a point. So then halfway between here, I'm at negative 1.5. Okay? So here's the good news. When I gave you the other ones, we did the 1/2, and I'm not going to make you do any of that. I don't think that that's that necessary. I wanted on the other ones so you could understand what was happening. But if you know what's happening with the asymptotes, if you just sketch this in like this, I'll be fine with that. Okay. It's like that. So then it repeats. I have an asymptote over here, and I have one right here. So this was down, up. This one's down here at 1.5 in the middle, up here at 1.5 in the middle there. Oh, goodness, that's bad. Don't make these look like little V's or anything. Like it's got to, make an honest effort to have a semi-decent graph. Remember, I don't want it to look like your pencil threw up on your paper. It doesn't have to be perfect, but you need to make an effort here. Okay, so there's that. All right, so now let's look at number 3. Let's do a secant graph. So secant, the period is 2 pi, but when I multiply it by 3/4, because it's dividing by 4/3, that's multiplying by 3/4, the period's going to become 3 pi halves. I do not have a vertical stretch or compression. It's 1, that number's still important to me. I do have a reflection, though. That's important. Secant is 1 over cosine of theta. Oh, cosine of theta. I'm trying to write pi. Cosine of x, really, here. And so I'm going to draw a little parent function of cosine, because that's going to help me get everything for secant in the correct places. So for cosine, I start at 0, 1. That is a point that the parent function shares with cosine. Cosine and secant both share that 0, 1 right there. But I have a vertical stretch. Well, I don't. It's at 1. But I have a reflection, so I actually end up down here at negative 1. Okay, and we don't have any shifts yet, so there's a point right there. The end of the period is also going to be right there. So at 3 pi halves, which is right here, I would be up here at 1, but there's a reflection, so I'm down here. Then I find halfway. Halfway in between was a minimum, becomes a maximum, right? Halfway in between is right here, so it'll be at 1 up here. I'm not drawing cosine, but those 3 points are the same. Then since these were zeros, this is where the asymptotes happen. In between, directly in between the two of those, I have an asymptote. And I have an asymptote halfway in between here. So there are my 5 key pieces, and I can repeat. Okay, so I end up with an asymptote here. All right, and an asymptote here. Then a point, then an asymptote, a point, asymptote, right? Okay, this point right here is wrong. This point should be up. It's supposed to be alternating. So it was up, down. I got to be up right here, then down, then up, down and up right here. Okay, I'm not doing the same blue curve here. Remember it's like an inside out. So once I've got all that, then this is what they look like. And there are your graphs. Okay, so we've done a cosecant and a secant. Let's do a cotangent. All right, so cotangent. The period is pi, but I have to divide by b, so it's pi halves. I have a vertical stretch of 3. This is 1 over the tangent of x. And when I draw in this little graph, now for cotangent, you could draw in a tangent graph if you wanted to, but cotangent isn't that bad. It's the secant and cosecant where the parent functions, I think, would just throw you off. Cotangent's pretty simple. It actually looks nicer than the parent function of the tangent. This is an asymptote, this is an asymptote, and it goes the opposite way of tangent. Okay? So drawing that one might be just fine for you here. Okay, so there's no shifts yet. So when we're here at 0, x is 0, we have an asymptote. The end of the period, so that's that. The end of the period is an asymptote. The period is pi halves. Asymptote right here. Halfway in between the two, we have a 0. Halfway in between these two would be at 1, but we have a vertical stretch of 3, so it's up here. Halfway in between here would be -1, but there's a vertical stretch, so it's -3. There are my 5 key pieces. This is the first section right here. Looks like that, and then I can repeat. So I have asymptote, point, asymptote, point, and the same on the other side. These points you do need to plot, and I make you plot all these points for secant and cosecant, but when you can plot them, you should plot them. And so here is tangent. Or cotangent, I'm sorry. There you go. We've done one of each without any translations, so now we're going to start shifting. But we will shift tomorrow, so I just hang on to this. You may or may not want to go ahead and glue or tape it in. It depends, because we're still going to write on this. But make sure that you get your get the homework from the substitute. Do the front only. Front only. Do it before tomorrow, get started on it, so if you have any questions, we can go over that in class.